Hello to everyone who are watching this video presentation created for the Current Research in Hydropower Technology Conference. My name is Ingelin Herland and I am a master student at the Norwegian University of Science and Technology, where I am studying energy and environmental engineering. And this spring I am writing my master thesis with the topic Design Optimization of a Francis turbine draft tube. This topic is the baseline for my presentation, but since my masterwork is still ongoing, I have not obtained all the results yet. So my focus will be to present to you my approach and strategy for solving this problem. I will begin with presenting the objective of my master thesis. Then I will further go on and discuss the main motivation behind this masterwork and present the most relevant theory. Before I, in the end, will talk about my method for solving the optimization problem. In verse, the objective of my master is the design and optimization of a high-head Francis turbine for variable speed turbine operation. Focus will be steady-state operating conditions of the turbine. So, my master thesis is written in collaboration with a HydroFlex research project, which is an EU project for developing more flexible design of Francis turbines. So, for my draft tube optimization, I'm using a newly optimized runner design for variable speed, which is developed as part of the HydroFlex work. Now, first of all, what is a variable speed turbine? Traditionally, hydropower plants are designed to operate at a fixed speed of rotation of the runner, or synchronous speed as it is called. The reason for this is that this produces power with frequencies which makes it easy to connect the hydropower plants to the electrical grid. This has resulted in that hydropower plants are designed to have their best efficiency point for a particular design speed of the runner and for a design volume flow. However, the increased integration of energy sources such as solar and wind power leads to more fluctuating power supply in the energy market. This stresses hydropower plants as they are expected to regulate the power supply by changing the volume flow. But these hydropower plants are more rapid operated outside design conditions, which again give rise to two types of losses in the runner: incidence losses at the inlet and swirl losses at the outlet. The philosophy behind variable speed turbines is by letting the runner speed also be a free parameter for regulating power supply, the incidence and the swirl losses of the runner can be reduced, and the efficiency of the hydropower plant operating outside best efficiency point will be increased. The draft tube is the pipe which is leading the water from the outlet of the runner into the lower reservoir. Its main task is to convert kinetic energy in the water at the runner outlet into pressure energy at the outlet of the draft tube. This increases the total power output of the hydropower plant, which can be understood by looking at how energy is conserved. Francis turbines are reaction turbines, which means that both pressure energy and kinetic energy is transferred from the water into rotational energy of the runner. The pressure at the outlet of the draft tube will be fixed by the static pressure in the lower reservoir, and the remaining kinetic energy in the water is considered as losses. By introducing a draft tube with a diversion cross-section, the flow will slow down through the draft tube, and the kinetic losses will decrease. Further, this forces the pressure to decrease at the outlet of the runner due to energy conservation of the water in the draft tube. This increases the overall energy transferred to the runner, and by this, the efficiency of the hydropower plants. For my optimization process, I have decided to use three parameters to describe the draft tube performance, which I will refer to as objectives. The first objective is the pressure recovery factor, which describes how much the pressure has increased throughout the draft tube. This reflects the draft tube main task, namely to recover the pressure in the water. And we get that a high pressure recovery factor means good draft tube performance. Secondly, we got the energy loss coefficient, which reflects reduction in the total pressure or the sum of pressure and kinetic energy losses. Intuitively, we want to avoid losses, so it is desirable to keep the energy loss coefficient as low as possible. This objective is widely used in CFD optimizations, but poorly used in experimental lab analysis, as it is difficult to measure the entire velocity profile at the inlet and the outlet of the draft tube. The last objective is the total volume of the draft tube. From an economic perspective, it will be desirable to have a small volume, as this will give low material and civil costs. To sum up, the three objectives I'm going to use is the pressure recovery factor, which should be as high as possible, the energy loss coefficient, which should be as low as possible, and the total volume of the draft tube, which also should be as low as possible. These three goals will not necessarily be achieved for the same design, so it will be important to discuss the best trade-off between these. I plan to do three separate design optimizations for three different operation points, corresponding to part load, best efficiency point, and full load. As you can see, the runner speed differs a bit since I'm using a variable speed runner. The different operation points will give rise to different flow conditions in the draft tube. Best efficiency point will give axial flow into the draft tube with low swirl, compared to operation at full load, which will lead to circulation of the water in the opposite direction of the runner, and operation at part load, which will lead to circulation of the water in the same direction as the runner. In total, I am using 11 design parameters together with a few design constraints to describe my geometry. The inlet of the draft tube is kept fixed for all designs to always match the runner outlet. The upper part, or the cone, has a circular cross-section with a diameter which is increasing linearly in the flow direction. The middle part, or the elbow, is defined by a quadratic Bezier curve which describes the center line. The cross-section area is gradually changed from circular at the inlet of the elbow to rectangular with two bowed sides at the outlet of the elbow. The last part of the draft tube, also called the exit diffuser, is constructed with gradually divergent cross-sections into a rectangular outlet area with bent corners. This video shows the interface of ANSYS SpaceClaim, which is the software I use to build CAD models of the draft tube. A Python script which takes in the different design parameters as variables is building the draft tube by constructing cross-sections throughout the draft tube, and then using a blending tool to create volumes between them. Here you can see a mesh I've used for some of my simulations this far. It mostly consists of hexahedral elements, but got some zones of tetrahedrons, as this opens the possibility to change the resolution of elements throughout the draft tube. In the cone, the resolution of cells are much finer to capture the complex flow field, as well as close to the wall, where the mesh is finer to better model the boundary layers. As a reference, a scaled version of the draft tube in Tokke Hydropower plant in Norway is used. And the reference designs are found from measuring the sizes of the design parameters at this draft tube. In my analysis, I've let the parameters vary plus minus 30% from the reference. This is called the design space of the optimization problem. I will need to choose some combinations of the design parameters I will run CFD analysis of. This step is called design of experiment, and there exist various methods for populating the design space into specific samples. efficient design of experiment method obtains sufficient information of the entire design space with a minimum number of samples. This gives good accuracy of the results versus CPU time required. For my problem, I have chosen to use Box-Behnken Design method. It is a three-level method, meaning that it uses combinations of the design parameters from three levels: an upper, a lower, and a center value. The center value will correspond to the reference value of my design parameters, and the upper and the lower value will correspond to plus minus 30% of this. Box-Behnken Design is only using a restricted number of combinations of the parameters. This will save time compared to, for example, using another design of experiment method, such as three-level full factorial design, where the sample consists of all possible combinations of the design parameters. Another benefit with using Box-Behnken Design is that this design of experiment method is constructed for further response surface modeling. Response surfaces are mathematical models constructed by doing least square regression. The idea is to create response surfaces of my objectives: the pressure recovery factor, the energy loss coefficient, and the draft tube volume. This will provide mathematical models of my objectives given as a function of my design parameters, which I can use for further discussion. To sum up, my optimization process consists of first making a parametric design of the draft tube and then selecting sampling points by the help of Box-Behnken Design. Further on, I will do CFD analysis of the different designs, which is the current step I am working on right now. I'm trying different setup of my analysis, and I try to see if it will be sufficient to do the simulations without the runner and the guide vanes, meaning with the draft tube geometry only to save CPU time. From the numerical analysis, I will construct response surface models of the objectives, which I will use for further discussion. The goal with the optimization is not to obtain exact draft tube designs, but to capture the most important trends of how the design parameters influence the draft tube performance. Additionally, it will be interesting to compare the result from the different operation points. Thank you for listening to this presentation of my master thesis. If you have any questions or comments, please contact me on the email shown on the screen.